So I think you were asking about what's in the GitHub. Is it what you're seeing? I've talked about it a couple of times. I'm happy to talk about it again. Have you looked at the documentation in the framework? Okay, so there are papers about it. It is based on a long series of course materials for distributed systems. Ellis Michaels down at the University of Washington developed this, and it in turn was based upon a course at Massachusetts Institute of Technology. I don't know if you've ever heard of MIT before, but it's a school that's pretty well known in the computer science field. And I'm not even sure whose distributed systems class it was, but they had a whole series of projects to implement different pieces. So Ellis Michaels built this Java framework that is built on top of what is known as a discrete event simulator. So in a discrete event simulator, what you have is you have a time-ordered queue of events. And it's all single-threaded, which is one of the reasons we like to use it. We inject randomness into this system by controlling where we put the events. So in other words, when you write a little piece of Java code that says send a message, what happens is the framework then says, okay, let me roll some dice and see when that message is going to be delivered. So let's say that we roll it and it says, I'm going to deliver this in 120 milliseconds. I take the event that represents that message's delivery. I say, put it into the queue at a time of whatever it is right now, plus 120 milliseconds, and then return back to your Java code, and your Java code then returns back to the event simulator. And what happens now is that it's just a little event loop, and it says, okay, what's the next thing on the queue? And the next thing on the queue happens at this time, so now we're going to set the clock to this time. So the reason that we use this is that the time is not clock time, it's simulation time. So if you have an event, let's say you start up this thing and you say, wait 36 million years, and then print out it's 36 million years later, and then that's the last thing that happens. All that's going to happen is that the event loop will pull that event out, set the clock to 36 million years from now, and say, it's 36 million years later. We can simulate 36 million years without actually spending that much clock time. So it's useful in that it provides us with this very controlled environment. We don't have preemption. We don't really have concurrency. What we have are coroutines, in essence. You have an event loop, it pulls an event out, there's a function or a method that it invokes in that function or method, passes some parameters to it. And in Java, it's easy, right? You just pass the object, and the object encapsulates everything. The code then, the method, then operates on that object, and you can decide to do things like create new events. If you send a message, that corresponds to creating a new event. But maybe you look at this piece of code, and you say, I don't need to do anything for this. So you don't create an event. So nothing new goes into that queue. When you return from your handler back to the event loop will then look at the queue, and either the queue has another entry in it, which it takes off, or the queue is empty. If the queue is empty, we end. The simulation is done because there's nothing else to do. So it's a very simple framework. What we were talking about on Tuesday were formal models and verifying formal models. So what I've just given you is a modeling tool. The reason we use this is because it makes it really easy for us to simulate behavior in a way that's somewhat controllable, yet we can inject very carefully calculated randomness. It's not unique to Java. You don't have to do this in Java. If you go look, you can find that there are really nice discrete event simulators in Python. Probably would have been easier and less heavyweight than the Java one. One of the benefits of using the DS Labs framework is that it actually has a visual debugger that will show you the sequence of events in the system. See, in real-world systems, it's really hard for us to reason about what order things occurred in. And that's part of what we're going to be talking about today, because this is where things start getting a little mind-bendy. Have any of you ever worked in concurrent programming or asynchronous environments? All right, I mean, I've written actual asynchronous code up large where you literally send, and this is the way the world works, this is the way hardware works. Anybody ever written a device driver or worked with a piece of hardware? OS 161, asynchronous I/O? There's multi-threaded, which kind of, sort of, vaguely simulates it. In real hardware, what happens is you send a request to the network card. And the network card goes and does it, and when it's done, it sends back an indication saying it's done. These are called interrupts. It literally is, at the very primitive level, it is an electrical signal on a bus that says, hey, I'm a device and I need your attention now. And then we get lots of these things and we say, well, we're going to organize them in some sort of priority list because I can't do everything all at once, so I'm going to take things in order of priority. Anybody ever heard of the x86 processor? It's made by this little company called Intel down in, actually I think their largest location is in Malaysia, outside Penang. Sorry? Oh no, they build all sorts of things there. They design boards and they do BIOSes and network cards. And I think when I was there teaching, I think it was actually a networking group that I worked with. So they did start doing assembly there. But these days they do a lot of engineering there as well. It's very large. It might be bigger than the Phoenix location. Intel's this company that was started in Silicon Valley in the early 1970s to build this crazy thing called DRAM. Maybe you've never heard of that. No, but they invented the process that we now use for creating DRAM. Before that, we used a different kind of memory called core memory, which were literally like little wires wrapped around magnetic cores. And DRAM was much faster and was much cheaper, and Intel made their name in making memory. So then they started making processors. Question? On the politics of silicon chips, well, that's a loaded question, right? There's so many different ways that we could approach that I'd waste all of the time, and since it's 5:01, I actually have to start really talking. So I'm still talking about a discrete event simulator. It's at least applicable to what we're talking about today. Processors are internally built to handle interrupts. So the way that we built hardware is we said, hey, we're going to put some devices on this hardware, and then we're going to have to control what interrupts we handle in what order. And so there's literally a way of masking and enabling interrupts. And the processor handles some or all of that. Over the years, that whole process of handling interrupts has become more complicated, but the underlying idea is I ask somebody to go do something, and instead of me checking with them every few seconds to see if it's done, are you done yet? Are you done yet? Are you done yet? I wait for them to raise their hand and go, yo, pay attention to me, I'm done. And there are some things in there that are really important that say, pay attention to me now. There's one interrupt called the non-maskable interrupt. It's the one interrupt that you can't mask on the processor. Turns out you can mask it elsewhere. So if it occurs on a peripheral bus, you can actually mask it on the peripheral bus. It's also a weird interrupt. I learned about this many years ago because there was a bug in Windows in the way they handled this particular interrupt. Microsoft said, gee, wouldn't it be nice if we could get a crash dump out of a system that was stuck? And so they said, yeah, we'll put this piece of hardware where you push the button, it generates a non-maskable interrupt, and that would jump to the non-maskable interrupt handler, who would then look and say, am I configured to take a crash dump on an NMI? And if I am, take one. The problem is that unlike every other interrupt, a non-maskable interrupt is sent to every single CPU. So We can't have every single CPU running the interrupt routine, so they contend for a spin lock, and only one of them wins, and the other ones sit there and wait until they can get their turn at the spin lock. The problem is that for all of the other interrupts, what happens when the system decides it's going to crash is it sends an interprocessor interrupt, which is just below the priority of a non-maskable interrupt, and says, yo, CPU, store your state in memory so it gets into the crash dump. Didn't happen in this. In this case, the NMI would fire, one of the CPUs would win the spin lock, it would ask everybody else to do it, but they were all blocking the NMI, or the IPI, the interprocessor interrupt, so you wouldn't get any of the other CPU state. It was kind of not very useful for doing exactly what they wanted to do, which was debug a system that was in some sort of a spinning lock condition. They actually had to change the interrupt handlers to deal with this special case. And I worked with a crazy group down in Mission Viejo at Unisys that discovered this and fixed it. Sorry? No, it's not. It's actually an electrical signal that changes, it literally stops what's going on in the CPU. It stores the state of the CPU at that point in time, and it transfers control to a piece of code that is specified in a table that says, when this event happens, go here, do that. It doesn't pull. It's actually electrical. It's actually using a signal. And when it sees this, maybe the hardware is polling for it, but the software certainly isn't polling for it. I mean, I don't know how the hardware people do it. Any ECEs in here know how? Right. So the point is, in the real world, things happen asynchronously, and we use interrupts and these other kinds of mechanisms to rendezvous back up when it's time to do something. In a discrete event simulator, we actually have a tight loop that's well controlled that doesn't actually allow concurrency. See, the benefit of having this interrupt-driven asynchronous model is it means we can do lots of things all at the same time, because I have several different controllers. I have one for the network, and I have one for the keyboard, and I have one for the audio, and each and every one of those has its own little piece of hardware that can be running simultaneously. It's literally concurrent. Do any of you know Sasha Fedorova over in ECE? Sorry? She taught you a course. Nice, nice. So Sasha Fedorova was heavily involved in the design and development of scheduling algorithms for multi-core processors, or hyper-threaded processors, actually, symmetric multi-threading. So the CPU folks said, we could actually make this physical CPU look like it's two virtual CPUs, or 8 in the case of the ones she was working with. So the benefit of that was that we could time slice back and forth on the hardware. And of course, we have the other approach, which is we can add multiple cores. And those are really, truly asynchronous. They're really independent of each other. Now, it's not like multiprocessors were brand new, but I can tell you when I started teaching Windows internals in 1996, talking to people about multiprocessor PCs was sort of like, people were like, what? What? Nobody uses multiple processors. And then multi-core showed up, and then pretty much everybody runs multiprocessors. Your watch runs multiprocessors these days because it runs multiple cores, and each of those cores is an independent processor. But that makes it really hard to reason about things. And that's part of what we're talking about in Chapter 8 of Petrov, is we're talking about concurrency. What does it mean for something to be genuinely concurrent versus what does it mean for something to be pseudo-concurrent versus what does it mean for something to actually not really be concurrent, but to kind of have this interleaved model. In the DS labs, the discrete event simulator is the latter case. It is we're going to pretend that we can do more than one thing at once, but in fact, we're going to give you sole and exclusive use of the simulator until your routine returns, and then we're going to pick somebody else, and they get sole and exclusive use. So there's no race conditions in memory access. That makes it pretty simple. The place that we introduce the randomness using the DS Labs tool, which is a discrete event simulator, is we randomize things like, what is the probability that this packet gets delivered at all? Well, this is a really easy one. You call send, and send rolls the dice and says, let's see, I'm going to drop 3% of the packet. So, I roll it. If it was 0 to 96, your packet went through. And if it's 97 to 99, sorry, your packet got dropped. You don't have to actually do anything. You don't even know that's going on. It's just some little tuning parameter in the framework. And the other piece of that is we've established a range of times that it could take for us to deliver that packet. That simulates things getting stuck in a network. It also helps us then see things that could occur out of order. Because remember, real networks don't guarantee ordering. We can build protocols on top of real networks that guarantee ordering, like TCP. But the network itself doesn't do that. IP doesn't guarantee that you're going to get your packets in the order in which you sent them. It doesn't even guarantee you're going to get them in the same size that you sent them in. IP packets can be fragmented individually into smaller and smaller units. If you really want to explore that, go do amateur packet radio, which has the smallest MTU I'm aware of. I think it's 256 bytes. You can send an Ethernet frame from your laptop or your Wi-Fi, and then it goes across an Ampere connection, and suddenly it's a whole series of 256 byte packets that have to be reassembled at the other end. And those can be reordered, and all of this stuff happens. So the DS Labs is a controlled environment for us to build a solution to a problem in this space. You don't have to use the DS Labs if you don't want to for the design project. It doesn't matter. The goal of the design project is to try and help you think about problems rather than try to code your way out of them. Because I will tell you that in distributed systems, you do not code your way out of them. I literally was just having a conversation with a friend this afternoon, and he told me about it. He does, he's only a couple years out of uni, graduated in 2020. And he said that something he did cost his company $150,000. He's like, I don't know why I'm still employed here. And I said, why would they fire you? They just spent $150,000 to give you training. Things break. Things go wrong. Happens in the real world, and it costs real money. To the point of the DS Labs, these are the same labs I used when I gave the class last term, and it's the same labs I use at the University of Washington for their distributed systems class, and other people use them. Georgia Tech uses them as well. The primary way that people use these is to give them to you and say, here, implement these. And the reason that I'm trying to de-emphasize this is because what that mostly leads to is people pounding their head into the keyboard trying to code their way out of the problem. You didn't come to UBC to learn how to be a code your way out of the problem type of problem solver. Maybe you've done some of that, but that's what they do at boot camps. What you need to leave here knowing, how do I solve bigger problems than I can actually code my way out of? Project 3 here, which is our design project 1, is not a really big project. It's a small project. It's small enough that I said you don't need a team for it. It's got what? Basically 3 components, and then there's a chorus of clients that do things. It's got a primary server, a backup server, a view server, some amorphous clients, and then you can have a chorus of servers sitting there hanging around going, hey, I have nothing to do. If you want me to do something, just let me know. Great. It's pretty straightforward. When people actually implement to this, the problem is it's the 3rd project they've done in the DS Lab series, and the first 2 are like so dumb. You're like, why did they give this to me at all? And you get to the 3rd one, and you go, this isn't so bad. I waited till the night before, and I got it done, and it was fine, and I passed the auto grader, and life is good. And then you come back 3 weeks later, because now it's the night before project 4 is due, and suddenly there is this big turd that falls out of the sky on your head. Because you have been sold the big lie that these aren't going to be very hard, and no matter how much I say, you won't believe me. Project 4 and 5, which are really the meat of what we're talking about in this course, are hard and really hard. And despite saying that, I will tell you they are super, super dumbed down samples of what you really have to do in the real world. The people who were most successful doing projects 4 and 5 are the people who designed their solution. And when their design didn't work, they iterated over their design and they went back and did it again. So what I'm trying to do here is help you gain the skills necessary to be able to walk out that door and say, I know how to approach the problem in a systematic way, and I may not get it right the first time, and I may not even get it right the second time, but I'm going to get iteratively closer each time. The problems in the real world don't get easier. They get harder, way harder. This is just a tool. What we talked about on Tuesday was formal modeling, verification. This is the modeling side of that. In fact, what the DS Labs does as part of the tests, it runs through what are called search spaces. It says, I can reorder your packets and I can deliver things in slightly different orders and I can inject a certain amount of loss and you should be able to handle it correctly. That's the benefit of DS Labs. It's a really cool tool for exploring the space of solutions to these problems. But I'm interested in helping you get the skills you need in order to be able to design the solutions. Your code's going to suck. There's just no way about it. How many of you have actually written production quality code? A lot harder than it is doing a student project, isn't it? They beat the crap out of you, don't they? And you get PRs and you get bug reports and you get people making you do things that stand up, like talking about what it is that you did wrong and whatnot. You have to do failure analysis and you're like, this is really hard. I've talked before about the stuff that I did, the transactional recovery system I built for Episode starting in like 1989. It's still in production use today. IBM still uses some version of it. I'm sure it's not exactly the same. It's been, no doubt, lots of bugs have been fixed in it. Systems code lives long, long time. Distributed systems code constantly evolves, but also lives a very long time. When you start looking at the distributed systems projects that are still in active use today, let's point at S3. S3 is more than 20 years old at this point, and it's still just a little bit in use. I'd have to ask Andy, but I'm pretty sure that there's probably close to a zettabyte of, I know there's more than many exabytes, if not close to a zettabyte of data just in S3. Adding new features, evolving things. Believe it or not, even though these things are old, there's a lot of pressure to constantly be improving them, adding features, functionality. New hardware technology comes along, and so you have to think about, how do I actually use this? There was a discussion last week about tiered storage. LSMs are real. We really do use them. Now, we might be putting S3 on top of an LSM, but as a client using S3, you don't even notice. And that's actually the biggest part about the job that makes it difficult, is often you are called upon to introduce additional new features in there in a controlled fashion so that you can verify they work correctly. And when they don't work correctly, you are going to be the one they wake up at 3 a.m. and say, we have a problem. And if you're working on Amazon stuff, that happens. People get what's called pager duty. They are literally on call because there's somebody using AWS 24/7 somewhere in the world. So that's what DS Labs are. I'm going to be talking about, I'm going to put this away now. I am going to be talking about the design project because I think that's one of the more important things that people are starting to freak out a little bit about. It's not very hard. It's not nearly as hard as the second and third design projects, but in the second and third design projects, you're going to be trading the fact that you have to do the design project by yourself with the fact that you now have to do it with other people. Blah, blah, change there. Post-self-assessment activity for today's discussion in Chapter 8, Part 1 is next Tuesday. I have changed the format a little bit. I put fewer reflection questions in there. They're all the same reflection questions. I just pick out of the pool and ask you to answer a couple of them if you're slightly engaged and interested. I did increase the number of content questions a little bit, and I put some false questions in there. It takes a lot of time to put those questions together. I'm always amazed at how hard it is to ask decent questions. Just don't forget to submit it, otherwise you won't get credit for it. Let's talk about Design Project 1 since we're already talking about it. Anyway, so what are my goals here? I want you to focus on designing. I had somebody ask if they had to submit their code, and I'm like, for Design Project 1, you submit a design. The code that you submit, I actually don't really care about, but it won't be for your own design. And that is probably going to be one of the cruelest things that I do to you in this class. But that's the real world. You usually don't get to implement your own design. You get to implement somebody else's design. And if you've not done a lot of design work, you will quickly realize that one of the meanest and cruelest things you can do, far crueler than anything I'm going to do to you, is to make someone else implement your design. Take your design, put it away, look at it in 5 years. And you're probably going to say, I can't believe I wrote this piece of shit. You'll probably say that about the code you write now, too. The only way in the end that you can actually learn this stuff is by doing it and seeing what works and what doesn't work. I mean, if I just simply gave you a design project, you'd be like, yeah, whatever. But you get to do a design project, and you're already going to be thinking about, okay, well, he's given me some evaluation, and I'm supposed to be considering other people's designs, so they're going to be considering that when they look at mine. So what can I do to make my design a little better? And then you're going to read other people's designs. You're going to go, wow, they did a really bad job on that. Oh, wow, I never even thought of that. That's a really good idea. You're going to be exposed to other people's ideas and thought processes. And in the process, unless you really don't read it and you just simply push the submit button, which is fine, in the process, you're going to absorb some of that. Then the hard part. You get to pick one of those 3 designs that you review and implement it. And you're going to have to say, and you know, you could be really tricky. You could say, I'm going to implement all 3 of them and pick the best of them, or the worst. I don't know which should be. Or you're going to be like a little more reasonable and say, I think this is the best of them, and I'm going to try and implement this and see what happens. And then in the end, you're going to say, wow, you know, this design was so good that I was able to get 75% with like 3 hours of coding. It was awesome. Or somebody else is going to sit there and they're going to say, you know, I spent 3 days and I couldn't get past 10%. It doesn't matter. You're going to get credit for it either way. But it's going to give you insights, isn't it? What do you learn from implementing somebody else's design? And see, he was trying to ask a question, and since he had his hand up and I got to ask him a question, it's a really dirty trick. What do you learn from implementing somebody else's design? Some of what they did right and wrong. You might identify things that they didn't even consider. Right. Right. So so, you know, the boss gave me this design to implement, and I'm looking at it, I'm going, I'm glad I didn't write this piece of shit. And instead you write the piece of shit code that implements this piece of shit design, and you evaluate that, and now you get to write back and say, this is what it should have been instead. So you see that now we get a whole loop here. You got feedback on your design, you gave feedback on this design, you implemented something, you wrote a report that said this is how it could be done better, and other people can look at your report and see what they can learn from it. And then we're going to iterate over this. When we go to Design Project 2, I'm going to let you work in groups, which creates a completely different set of problems, which, how many of you have done group projects before? How many of you like group projects? How many of you hate group projects? How many of you are ambivalent and don't care? See, it's like a third, and a couple of people raised their hands twice or 3 times. So it's great. I love it. So I don't really care whether you do the second and third design project on your own or in a group. You could do the capstone. You can do it on your own. Some people are really good at that. If you're really experienced, you know, oh, I've been doing this before. I've done designs. I know how to write code. I don't want to to be the carry for somebody else. Do it yourself. That's great. I'm actually thinking that what I may do is ask a couple of different people that do work in this field to look at the final capstone projects and to pick a winner. To say this is the most impressive of the capstone projects. All you get is a feather in your cap, but at least there's an incentive. And I'm good at creating artificial incentives that don't really have any meaning in the rest of the world because I play video games. Was that your question? No. May I ask you my question? Yes, you may ask your question. Next question. What's your question? I don't. I mean, so if you wanted to minimize the amount that you learn and you just decide you're going to implement your own design, somebody else's. Yep, right. And so you decide that you're going to cheat and actually, okay, fine. It's all right. If you're writing a design that's so much better than what other people gave you, but no, and I thought about that too, and I was like, do I care? Does it change the learning outcome? Not really. Learning outcome is for you to do better designs. The reason I'm forcing you to do somebody else's design is because that way you can understand what it's like to suffer with a bad design. Because my assumption is that 80% of the designs that people pump out are going to be, what? Pieces of shit. Right. He says trash. He's the polite one. And 20% of them are going to be pretty good. And you're hoping, oh my God, I hope I get one of the 20%. I hope it's better than mine. So if you end up looking at 4 designs and decide yours is the best of them and you implement it, okay, you've learned something, haven't you? Hey, I'm not so bad at this. But don't worry because the pressure's going to ratchet up. Because people are going to get better. Second design project, the designs will be better. Most people will actually write better designs because they're going to be going, yeah, I mean, I suppose I could just click the boxes, in which case then you're not going to do anything anyway, and I don't care. They don't care. If you want to learn, though, you're going to look at what other people did. You're going to look at the design documents that we do publish, we share with you, and you're going to skim through them, and you're going to say, oh, I like that one. Because there's going to be, except for maybe one person in here, there's going to be somebody else who did a better design than you did. And even that person, my guess is that probably they'll look at other designs and say, oh, there's still some good stuff in here. This is ensemble learning for humans. In case you've ever heard that term, it's a machine learning tool where you take lots of weak classifiers, bundle them together, and magically you get something better than any one of them was individually. Vaguely sort of hand-wavy like that. So I want you to learn by doing it. I want you to learn what works and doesn't work. The point of the peer feedback is that I actually expect that some of this is going to be a struggle the first time. It's cruel. I told you that. But making somebody read your design document that you wrote that's a piece of shit is also cruel. And I'm doing that as well. So you're suffering along with everybody else. And I'm not a big fan of suffering for its own sake. I think in this particular case, it has a purpose. And that is, see what works, what doesn't work. Then you get to implement it and see, was my intuition, was my initial analysis correct or not? Maybe there were things that when I looked at that design first, I said, this is really stupid. And then I got into the implementation and went, I see it now. This is actually really good. Or, I thought this design was really good, but there were a whole bunch of cases they didn't think about, and they weren't baked into their design, and they really needed to step back and do a better job of defining their model in the first place. And then the implementation report is, how would you make that design better? I've now implemented your design. I took your piece of shit. I created something that vaguely looks like the Mona Lisa painted with feces. And here is what I would do. I put some ochre in the feces. It would make it closer to the color it needs to be. Whatever. Doesn't matter. It's the introspection process. So in the design, what do? People are going to be sitting there, oh, I don't know. How many of you have actually done a real design before? As opposed to, like some half-assed experiments in class, right? So let's walk through the process, right? Identify a problem. What do you think the problem is? What are the components in this system? How do they interact with each other? I mean, if components don't interact, hey, I got two clocks on two walls that don't have anything to do with each other. Not a very interesting system. Don't really care. It becomes interesting when they start to interact. What do those interactions look like? What are the challenges here? What failures do I want to handle? I've already talked about the network failure. That's really the big one. Network failure, machine crash, simple things like that. And part of what Petrov talks about in chapter 8 are failure models. And he says, hey, here are the kinds of things that we think about. What are the guarantees we're giving to our clients? We've got this CAP theorem thing, which we'll keep coming back to, which is consistency, availability, and partition resistance. And the P turns out to be kind of independent of the other two. You get to pick CP or AP, but nobody picks CA. That's kind of dumb. And you don't get all three together. Well, you can claim to get all three together, but then it just becomes marketing fluff because you can't have consistency, availability, and partition resistance with all three. What are our desired outcomes? What do we want to do? What is the guarantee we're providing the clients? Understanding what the clients are expecting helps us establish what our expectations are. What are our performance and scalability expectations? This must be available 99.99999999999% of the time. Okay. Well, let's see. That will be $99.999999999 billion. How many of you would think your job was in jeopardy if you made a $150,000 error? How many of you have made a $150,000 error? Yet. Come back in 5 years. It's also important to establish what the non-goals are. What am I not trying to do? It's really easy to say, I want to handle all failures. Well, okay, then I'll give you the Marvin the Martian video, which I played last term in class, which is from the 1950s, and it's Marvin the Martian blowing up the Earth because it obscures his view of Venus. And Bugs Bunny, of course, has to save the world. It's a cartoon. You can't protect against the destruction of the Earth. Well, you could. We could design an entire system. It would be a lot of fun. It would be a very interesting academic exercise, but you're not going to get anybody to pay you to do that. The closest I've seen anybody get is the $5 million investment for that company that is designing a lunar data center. That almost makes sense. It's probably not necessary to solve the problems in any of our design projects. I don't expect you, although it could be a cool capstone project, to design a lunar data center. That could be really cool. And, provide a simulation of it and show what it's like and what the characteristics are. And then you could go to that startup company that's got $5 million as well, $4 million, because, they had to pay some executives. They could pay you $150,000 to work on that project. That almost would let you rent like a bachelor suite in Poco here. Almost. Step 2, let's propose a solution. Provide enough detail in that solution that somebody else can understand it. That really is what I'm hoping your designs will get to. Someone else can pick this up and they can understand what do the components do and how does the data flow between the components? What is the control flow between these components? Pretty straightforward stuff. Don't be afraid to draw pictures. I hate flow diagrams, but I draw them because they can help clarify what's going on. State diagrams can be interesting for small state spaces. If you've got 100 states in your state space, you probably don't want to be sitting there using Tixie and LaTeX building state diagrams. Well, it's 20. And they look really cool. They just spend way too much time doing graphics, diagrams, LaTeX. Anybody ever use Pixie? Anybody ever use LaTeX? I've used both. One of my few open source contributions was to matplotlib to Tixie, which takes matplotlib and turns it into Tixie pictures. They're very nice to put inside of LaTeX documents because they're scalable. Make those pictures really, really tiny. Please pull out your electron microscope so you can read figure 2713. They discourage those kinds of pictures in papers. Architectural diagrams, big block diagrams with sort of the breakdown of what the pieces are, can be helpful in people understanding what your vision is of your project. Modular decomposition is your friend. Take big problems, break them into lots of small problems. Take smaller problems and break them into teensy-eensy problems. And now suddenly things start to look solvable. About what the modules and components do. None of this should come as a surprise, I hope. Like going, oh, well, yeah, this kind of sounds like software engineering sorts of topics. Yes, well, design is a software engineering activity. How are you going to evaluate your solution? It's one thing to say, this is how I'm going to build it. Then how are you going to validate it? That was one of the reasons I tried to get Finn in here early. I want you to think about what tools could I use? Do I expect you're going to go off and build cock proofs for your distributed systems designs? Probably not. But if you do, I'll be really impressed. If you want to learn TLA Plus and you want to do your capstone project about designing something with TLA Plus, I think it's great. I would not discourage you from doing that at all. The goal is to learn how to do better design. And learning how to use tools that help you do better design is definitely meeting that learning objective. So how are you going to figure out if it's working? Go back to your goals. How do I know if these goals were achieved? Maybe I had nebulous, fuzzy goals. Well, this is where you get to nail them down and say, what does that mean? It's really pretty. It has a very complementary palette scheme in the diagrams of the design. I don't know. Maybe that's how you evaluate it. I'd kind of laugh if that's the way you evaluate it, but I'm not going to say it's wrong. These are distributed systems projects, so most of them aren't going to have like really fancy GUIs or anything in them. So you don't have to worry about that. And this is a systems class, and systems people think that the only GUI you need is a command line. That's what God gave us. That's what we should be using. What metrics are you going to use? Latency. Latency is a great one. Latency means how long does it take to process a request, and you can look at what the average latency is. Actually, in distributed systems, it turns out that tail latency is a really important thing, which says, I complete all but some tiny fraction in this amount of time. And this is kind of what happens when the system melts down. That's when the tail latency spike and suddenly everything takes forever and nothing actually happens. And that happens in real-world distributed systems. So they measure tail latency. Do we have stragglers? Do we have pieces of our system that are running too slow? How do we identify those? So it's going to move beyond just your design. Understanding these ideas of computing latency and monitoring latency and measuring latency will be generally useful, not just for design. Throughput. How many requests can I handle per unit time? Availability. What's the uptime? All right. I mean, this one, you're probably not really going to measure your uptime. Well, I got it up long enough for me to get my numbers so I could put them in my report. Done. That's academic. That's what academics do. When they write papers, it's like, put that system up long enough for me to get some numbers so I can put them in a chart so I can publish a paper and move on. In industry, that's not the way it works. They're going to actually keep measuring. What is our uptime? What happens when things go down? How long did it go down? Why did it go down? We're going to do failure analysis. We're going to look at that. We're going to have monitors running all the time, and there are little alarms that go off, and they page you at that inconvenient time when you're just getting frisky with your significant others. I didn't want to be very specific there. Oh, look, I've got my cats. And then you have to go work. Imagine, you could be the person who was working for Facebook when their data center became unavailable and somebody said, you have to go to Menlo Park. It's 2 in the morning and I live in Livermore. Well, at least there won't be a lot of traffic. Only take you 2 hours. What is your availability? What is your consistency? Consistency is actually really important because consistency relates to, is my database scrambled or not? That's kind of the coarse definition of consistency. Database not scrambled, consistent. Database scrambled, inconsistent. Inconsistent is bad. Where's those backup tapes? In Design Project 1, the problem that you are designing for is laid out in the DS Labs primary backup replication project, which is number 3 in that repo. The other stuff is just there because I have it all. I might as well give it all to you so you can see the framework. You can play around with it. You don't get to assume that people did projects 1 and 2 because they didn't. We didn't ask them to. Oh my gosh, you mean I have to put a hash map in there? Yes, there's about 10 lines to put a hash map in. It's not very hard. It's not going to be a major part of your design. It will not make it significantly more difficult. A hash map is the Java term for a key value store. This is the best part about computer science. We reuse names over and over again to mean different things. And then we use completely different names for pretty much the same thing in different domains. And this is how we keep out undesirables, the people who don't understand our language. Humans do it all over the place. We do. We actually invent this weird-ass language so that it keeps newcomers out. You don't have any idea what people are talking about. Go listen to doctors sometime. Talk to Andy, the TA. He's a med student. He can confuse you. Tell you about all the strange lingo they use. Latin? Who uses Latin? It's a dead language. The Romans have been dead for thousands of years. How many of you speak Latin? Great, nobody. How many of you speak English? 2 people raise their hands. Great. How many of you speak Spanish? How many speak Mandarin? How many speak Cantonese? How many speak French? There you go. How many of you speak Latin? None, and yet that's the language the doctors use. Go figure. So we get to speak computerese. We talk about Paxos. Other people will think you're talking about a Greek destination for a wonderful holiday, and here we are going to teach you about olive contracts and priests and agreements and legislatures that operate asynchronously. You are not implementing design. You are not implementing this project for your design part. You will get a chance to implement somebody else's design. At least that's the goal, unless you're one of these insidious people who decides that they're just going to go and implement their own because it's better. That's fine. Or, if you're going to do that, you might as well just simply not implement anything at all and just submit some code that doesn't even really compile, and you'll still get credit for it. Because I don't care. I only want to help you learn if you want to learn. Great. So that's the intro to Design Project 1. I know that you will start thinking about that and going, oh my gosh, and you'll put it off till the day before, and then you'll work on it. That's fine. Don't do that for the capstone project. I'm going to start pushing some project ideas out here and there about things you might want to consider doing for a capstone project. But those aren't intended to say these are the only choices you have. Instead, they're intended to say, hey, I can't think of anything better, so I'm going to take that stupid idea that the prof gave and pitch that as my capstone project. Last term, I had a couple of students who did some really interesting projects with, like distributed messaging, and one person worked on an open source project called Roy. You want to go work on an open source project for your capstone? I'm all for it. It just has to be related to distributed systems, which is a pretty broad field. Talk about failure. Today's failure is brought to you by Cloudflare. Who knows what Cloudflare is? About a third of the class. Great. What's Cloudflare? CDN. See, what did I tell you about language? Might as well have been Latin, right? CDN. What does CDN mean? It's a key value store. Content distribution network. CDN. It means let's cache the shit that you want on your computer close to your computer so it gets there faster. It's a web cache. It's a key value store. You know what the most commonly used model for building these content caches are? Something called memcached. It doesn't even preserve it. It doesn't keep it on disk. It just puts it in memory. So they build these servers with huge chunks of memory. They put them out in data centers near the edges of where people are, and then they cache stuff in them. So that when you ask for it and it's not there, you pay the penalty of going and fetching it because you have to wait for it to show up. But then he comes along and he says, yo, I want the same thing because I'm playing that really new, hot, cool game too. Boom. He gets it in like a tenth of the time. When you move around the globe and you're surfing the web, the stuff comes from different places because it puts it close to you. Now, what does close to you mean in a network? What are we measuring when we measure distance? We're talking about physical distance on the globe, right? No. No. It's a network. Anybody in here play games, video games, like competitive video games, like, PvP games or anything where there's like reaction times are important? What's the number that you care about? Latency. What's my ping time? How long does it take me to get my answers back from my packets? So really what we want is we want smallest latency. That's why latency matters. Otherwise, you want bandwidth? Oh, heck, let's just go get a van, fill it full of SSDs, of chunks of data, ship it to the other side of the country. More bandwidth than you're going to get out of the internet. The latency sucks. You don't want to play games over that. I've gamed over satellite. Old satellite, not Starlink satellite, like old satellite. 600 milliseconds. There and back again. It's not fun. Cloudflare, content distribution network. Cache stuff on the internet, make things go faster. Huge business, probably one of the best places to set up your DNS as well. 1.1.1.1 for your DNS server, and you're using Cloudflare. 8.8.8.8, and you're using, anybody know? Google. 8.8.8.8 and 8.8.4.4 are Google. But Cloudflare is 1.1.1.1. And if you're really smart, you don't use either one, you set up your own pie hole. Anybody know what a pie hole is? Anybody hate advertising? Pie hole is your own DNS server that actually sends back bogus IP addresses when they do DNS lookups on known advertising sites so that it doesn't break, because it doesn't look like you have an ad blocker, but the ads don't show up because they're not being fetched. It's cool. Probably, but they're probably not running a pie hole. The pie hole actually pulls a blacklist, so they know where the advertising content is stored, and they blacklist it, and it gets regularly updated. Like you can put it on a Raspberry Pi, which used to be cheap, and now are like $300. So you take your 5-year-old or 8-year-old, 10-year-old laptop, or you borrow somebody else's laptop that you notice in the, in the library. Huh? I needed a pie hole. There you go, perfect. Put Linux on it. Put a DNS server on it, you're good to go. Cloudflare had a partial switch failure, blah, 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 yada, yada. I'm not going to go through this in great detail. It's interesting, but it basically was an interesting network failure that they then classified as a Byzantine failure. The fun part is that their etcd is a configuration server. Kind of like a glorified or fancy view server, which is going to be seen in your first design project, because there are 3 components in your first design project. There's a view server, a database, a backup database, and a bunch of clients. Well, etcd is kind of like the view server. It's a configuration server. It uses the Raft consensus protocol, and this kind of fell apart because they ended up with split brain. And I mean, it was an interesting piece of analysis. There are a number of people who analyzed it afterwards and said this doesn't really fall into the Byzantine fault world, but it's pretty cool. It's a nice example of a failure. And guess what? It has a key value store called etcd. A database. A replicated database. It took them, what was it? So that was November 2nd, 2020, 2120. So it happened at 2 in the afternoon, and they recovered around 9:20 p.m. Not bad, 7 hours. That's a pretty good recovery time, but that gives you the idea. That kind of screws your tail latency times for a long time. A couple of years. You don't get very many of these without violating your service level agreements. So what is it I wanted you to get out of Petrov chapter 8? See, I said, okay, well, what do I want you to understand? Concurrent execution. You guys execute concurrently. He sits there, types on his mouse, you sit there, you cross your arms. You're both doing these things at exactly the same time. They are happening at exactly the same time, and I can observe both of them from my vantage. I see him slightly faster than I see you, but the slightness is so small that it is below my ability to perceive it. Does anyone know how far light travels in a nanosecond? Grace Hopper used to walk around and hand people pieces of copper wire that happened to be 22 centimeters long, roughly. Because that's the distance that light travels in 1 nanosecond. So that's why I say they're so close that I can't really perceive the difference. The farther the separation is between them, the harder it is for me to see them at the same time. If he's close and he's really far away, I will see what happened to him before I see what happened to him. So now we have a time problem, a time dilation. For short distances, it doesn't matter because it's in the noise of what we can perceive. As that time increases, it becomes more and more difficult for us to reason about these things. Anybody ever heard of this field called astrophysics? There's this interesting telescope they put up last year that is sitting out in a Lagrangian L2 orbit, a magic place away from the Earth and around the sun that means that it stays the same distance as we travel around, and it has lots of nice properties, and yada, yada, blah, blah, blah. Well, one of the things that telescope does is that it measures things that are very far away. We literally look back into the past. How long does it take for sunlight to get to the Earth? Approximately 8 minutes, right? How long does it take to get to Neptune, which is currently the farthest out planet, whether you count Pluto or not? It's like 22 hours. It's a long time, because it takes like that long now for us to talk to the Voyager space probes, are actually, I think, beyond that now. I'd have to go look up the number, but the point is that it's a lot longer. So when we see what's going on Neptune, we're seeing what happened yesterday. This is why I like the example of the lunar data center and the Martian data center, because all of a sudden it becomes really easy to think about minutes. So it's seconds to the moon and back, right? It's like a second, or yeah, I think it's a second or 2 seconds to the moon and back. It's 8 minutes to the sun. It's, I don't know, let's say anywhere from 22 minutes to 2.5 hours to Mars. So the nice thing about this is it's really easy for us to think about that in our frame of reference and say, seeing what happened 22 minutes ago versus seeing what happened 8 minutes ago versus seeing what happened a nanosecond ago are all very easy to realize they're going to be different. if what we're seeing are messages. This is going to make our reasoning process harder. Your message gets to me in a couple of nanoseconds. Anybody been to Mars before? I have, but it was Mars, Pennsylvania. I don't think that quite counts, but it's still farther away than. It takes a lot longer for my messages to get from Mars, even if it's just in Pennsylvania. And it takes even longer for them to get from Neptune. So I can't see exactly what happened at the same time just based upon me seeing what I'm observing at the moment. Honestly, what I have to do is I have to actually kind of snapshot over time and try to reason about it. So we have things that happen concurrently, but we can't observe concurrently. That's what distributed systems do. And this is part of what makes it really hard to reason about shared state. We're replicating databases. We're just simply trying to replicate a database. Let's make our database super simple. What is the simplest database you can think of? How many things do you store in your super simple database? 1! All we have to do is agree on one thing. How hard could that be? I mean, we're so easy. It's just one value, just one thing. But, nanoseconds, minutes, hours. I reason about it. How do I build shared state in this environment? I haven't even added packet loss yet. I'm just simply talking about latency. And this leads into that whole observation about how time is actually relative. There's this crazy dude with the wild hair. He's dead now, but you may have heard of this guy named Einstein. From what I've read, and I started out in physics, so I actually still have a love of physics. From what I read, Einstein's work on Brownian motion, technically one of the things he received the Nobel Prize for, and his work on special relativity would have been done whether he had done them or not. But his work on general relativity probably wouldn't have been done because no one else was there. It is really his work on general relativity that was both the most controversial, and it was specifically not named when he received a Nobel Prize. And yet it's also been the most enduring. We haven't found any holes in that theory yet, and we look really, really hard. So for example, has anyone ever heard of the global positioning satellites? This is how we know where you are. Well, that and the phone that you carry around with you. They conspire together to give us very precise location information about where you are. You may not realize this, but the clocks in the GPS satellites actually experience time dilation. And we know that. We can measure it. It's not huge, but it's significant enough they have to correct for it. Wow, that's kind of cool, isn't it? What we're talking about is, in essence, relativity for computer scientists. I can't observe the universe because it's not all equidistant from me. And equidistance here is measured in terms of latency. How long does it take for me to get that? I mean, it's really weird when you get into the quantum mechanics stuff and they start talking about how, they talk about probability clouds, but in fact, there's also this whole idea that until you can actually measure something, you don't know where it is. So it's the observation of it that fixes it. And in some ways, that's what happens in distributed systems as well. We start to try and realize that time isn't an absolute. It's relative to my frame of reference. It's relative to what I see. So the order of events that I see, messages coming in, is the order I saw them arrive in. Now, if you're all equidistant, then there's a certain amount of randomness there. There's a small amount of jitter. But things in the network aren't equidistant. And equidistant here means they're not exhibiting the same latency. It doesn't take the same amount of time. And this is a mind bender when you start thinking about, okay, so how do I take a snapshot in time? We can build a tool like DS Labs, and we can freeze it, and it will give us the ability to look at a system that is mimicking something with different latencies and different behaviors, and give us the ability to create those snapshots in time. So we do it by creating a model that lets us reason about this. But in the real world, we can't do that. So there are techniques for us to figure out what an order of events might have been. In this regard, it starts to feel like particle physics to me, because we know that these three things happened. We just don't know exactly the ordering in which they happened, but we came up with the same outcome regardless of which way they happened, so it doesn't matter. And I've mentioned this term before, isomorphic. I talked about schedules. Schedule is just the mean, it's really just, these are the events I saw. This is the order in which those messages got to me. How do I reason about what happened? And how do I take somebody else's schedule and make sure their reasoning ends up with the same outcome? Remember, we're trying to replicate state. I don't care if you process message A before process B and you do it B before A, as long as our outcomes are the same. And that's really the heart of the distributed systems problem that we're going to wrestle with for the rest of the term. How do I do that? And what we do is we create the super cheesy clock. Brought to you by Leslie Lamport. It's a Lamport clock. And in the 70s, so that was like, I was a little kid then. That was a long time ago. Lamport wrote this whole thing about time, and he talked about time, and he talked about how you reason about this stuff. And he observed that we can reason about time in a distributed environment with different latencies as long as everyone who sends a message has a clock. And that clock must guarantee certain properties. It must guarantee that it is monotonically increasing. It never rolls backwards. It never reuses the same clock value twice. And it turns out that means it can't really be used. We can't use the clock on our computer. Anybody know why? We adjust our clock. Our clock is a virtual quartz crystal oscillating at some level, and it has a certain amount of imprecision in it. And so what your computer operating system is doing is it's synchronizing your clock constantly. And might move it forward a little bit and move it backwards a little bit. And there's a failure where there was a bug in the Linux clock stuff that triggered when there was a leap second, and it did bad things. So we can't use the clock on our computer. Did anybody in here ever study TCP? How does TCP define the sequence of packets? Gosh, I used half of the term already in that question, didn't I? What does it use? And what is a sequence number? A tautology is something that's tautological. Okay, what is a sequence number? Give me an example. What did I say that we needed for a Lamport clock? Monotonically increasing. What is a TCP sequence number? Monotonically increasing. Wow! Oh my gosh, it's almost like we planned it that way. Right. So now we know the order of the packets because we just simply added one to them. You don't have to add one. You can add 3, 5, 7. You can use the Fibonacci sequence. Just don't use the first value. Right? Because it's 1, 1, 2. So you can't do ones. So, 1, 2, 3, 5, 8, so on. That works. It's great. Life is good. That's all it takes. And what's surprising about this is it gives us an awful lot of ability to control that. And what's going to happen is that when I'm sitting here at a node, I'm going to start getting other people's sense of time as well by watching the sequence numbers that are attached to their packets. So I have a clock, you have a clock, he has a clock. We're trying to reason about something together. Remember, we've got a one-entry database we're trying to synchronize. You say, here's what I think the value is. He says, here's what I think the value is. And I say, here's what I think the value is. And we each put our sequence number in there. We each get our own sequence number. So the sequence number is really, who am I? And here's my sequence number. See, this is the sleazy part about it. Lamport doesn't really use numbers, he uses strings. You're like, Really? When we look at viewstamp replication, which is a replicated database view server, we pick one node to propose new values because it simplifies our analysis a lot. And the way we pick it is by taking the node with the highest network address. What's the problem with that? What protocols, what network, what IP protocol do you use on your laptop? I don't know. 23? 42! No. Anybody know what IP protocols are in common use these days? There's a very tenuous hand in the back going, oh my God, we talked about this in 317 and I forgot about it because all I did was memorize it for a test. What? 4 and 6. And 6 was developed by a UBC undergrad after he graduated from UBC. I think he lives in West Van now, on a very nice house on West Marine Drive with a yard, a big yard, and a view of the water. Turns out inventing IPv6 was very good to him. I have to reach out to him and see if I can get him to give a guest lecture. He was always a really cool guy. Right, so I have different network addresses. Which one do I use? They're not even comparable, are they? They're not even the same. Well, I suppose I could just simply turn them into binary numbers and compare them. That way the IPv6 addresses would always win, because they're 128 bits versus 32 bits. I'll almost always win. Okay, fine. But you kind of get the point. It's like, oh yeah, this doesn't really work so well when we have heterogeneous networks, does it? So strings make just as much sense as anything else because that kind of just converts it into a binary number and we just compare it that way. Great, that's fine. Okay, so now we have a way of reasoning about this. As we start to communicate, I can keep track of the last packet I saw from you. So I can say the highest sequence number I saw from you was 42, and then I saw 39 from you, and I saw 117 from you up there. And now I can send my message and say, here's my clock, and here's the clocks for these other nodes that I've been talking to. And now we get what's called a vector clock. It says, this packet I saw, and it showed the state relative to these other people at this point in time. And what's weird about this is it's not really a point in time, right? It's kind of a point in time. And I can kind of reason about these things. And it turns out that kind of is actually super powerful. It gives us CRDTs, which are a replicated data type. Consistent replicated data types. And it deals with a branch of mathematics called lattice theory, which is partially ordered sets across a graph. And it's like, oh my gosh, my brain starts to melt down every time I go and read lattice theory. It's like, oh, wow. Or something altering, because it is pretty cool, but it's mind twister. Okay, fine. So at any rate, we have some techniques. I'm not going to dive into those techniques because you're not going to remember them anyway, but we have some techniques for reasoning about this stuff. And I am going to keep coming back to these techniques because they're going to become important as we begin to develop our protocols. Consistency is this idea that we all agree on what the value in the database is. Remember, it's our one-entry database. It's not a very hard decision to make, is it? And yet we're going to spend a lot of time walking through how Paxos agrees on this one entry. How hard could it be? All agree on the value at some point in time. Now here's the really weird part. What does that mean? You just got done telling me that time is all relative. Yes, absolutely. And that's why we have eventual consistency, which means at some point we all agree on this value. If I froze the universe and checked that value right now, it might not be we all agree on it right now, but if I let the universe proceed, at some point we would all agree on what that value was at some point in time. This is why they say eventual consistency means it's never actually consistent, but kind of, sort of. It's that very precise definition. Getting strong consistency. What does strong consistency mean? It means if we froze the system now, we would get the same value from all of the copies of our database. When we live in a real world where we can't freeze the system now, we have to reason about it. We have to say it is the same value. How are we going to get there? That's the question you're asking yourself. How am I going to get here? I'm actually reordering the chapters. I don't know if you noticed, but I'm slipping 14 in after 8. And the reason for that is because you need to know Paxos before you can do Design Project 2. And Paxos is covered in 14. But it is a solution to exactly the problem I just described. What is with the flaky graph? Must be that NVIDIA 3080 in there. Either that or it's the AV. So we have to worry about consistency. What does that mean? And we've got at least a basic model there. Now we have to start thinking about failures. Well, what could cause us to have problems in reaching it? Because in fact, in the real world, when we build a replicated database, what mostly happens all the time is that we all agree on the value, like within a very short period of time, of observable external time. And it's fun when you take like one of the Paxos simulators and you do the voting protocols, or you take the raft visualizers and you do the voting protocol and you see boom, 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 all these packets flipping around in your web browser, and then everything's settled and everybody agrees on the same value. And that's actually what really happens almost all the time. What makes it not happen are failures. What do you do when one of the nodes is offline? What do you do when there's a partition in the network? What do you do when somebody crashes, or the hardware melts down because there was a fire at that particular data center, and that node's never coming back? And you have to start thinking about what are these failures and how am I going to deal with this? And that's what Petrov is talking about. He's giving you a model for what these failures are like. And then, okay, now we have to talk about handling these failures. And then finally we talk about network stuff, because that layers right into distributed transactions. So we have this very generic model of a network where we have links, communications links that we can send messages over. The messages are not guaranteed delivery, not guaranteed ordering, but they are guaranteed to be all or nothing. So we don't get corrupted messages. That's Byzantine, and we'll touch on that later. So that's what I want you to take away from this. And that led us into the two generals question, or the two generals problem, which is this thought experiment that basically says if I have messages that go back and forth, it isn't actually possible for me to ever agree on anything, because I could be losing the answers. And this is why we try to use reliable communications like smoke signals. Things that I can observe that can't be blocked. And I think the reason they use generals is because it's nice. It creates exactly the scenario you need in order to explain why the messages might not be getting delivered, because they're getting intercepted. And no matter how many times you retransmit, you never guarantee that any of your messages are going to get through. You can't come to an agreement there. In some ways, this is going to lead into what we're going to talk about next Tuesday, and that's going to be the FLP theorem. Because FLP is the formalization of this model and the evidence that you can never achieve consensus in a network with a single failure if you really have total asynchrony. And so what we're going to do is say, gosh, why am I studying this? There's no solution to this problem. We're going to cheat. And the way we're going to cheat, we're going to use proto-matter to build our planet. Never mind. It's a Star Trek reference. You're too young. You wouldn't remember Star Trek. We're going to cheat, and we're going to time-bound things. So we're going to argue that we're allowing some level of asynchrony, but not a complete and total level of asynchrony, and that's going to get us out of the doghouse in this particular case. Anybody have any questions? Anybody read chapter 8? cool. Actually, that's like a third of the class, which is better than I thought, because you're all sitting there going, I got the whole weekend to read that, right? And then next time it'll be FLP, which is way denser and harder to understand, and you'll have 2 days to read it. But deadline scheduling for the win. Because if not, I'm going to just call it a wrap here. I think that we went through a lot here. Hopefully this will, if you haven't read it, hopefully this will help you know what you should be trying to take away from this. If you have read it, hopefully this maps into the, oh yeah, I totally get this, or I probably should go back and reread that bit. The assessment should open in 15 minutes. I've set it up right. And you'll have until next Tuesday. Like I said, it's a little bit different. I put fewer of the kind of general hand-wavy questions and do more of the specific questions. If you keep repeating it, apparently it will change the questions it asks you. There's supposed to be 6 true-false questions and 6 multiple-choice questions. I asked it to pick 4. Get roughly a third each time. Anybody have any questions? I can hear people already wrestling, going, oh my gosh, it's dinner time. I got to go find what we're going to eat. We got to reach consensus on dinner, which is going to take at least an hour. And then, and then you order it. And then it takes another hour to show up. And then, of course, you have to be waiting outside because otherwise somebody will steal your food. This is the advantage of living downtown in a high-rise, is they bring it right to my door. It's great. I've never had my food stolen. Not once. And my rent's probably cheaper than yours. I've been there for 12 and a half years. That's kind of sad, isn't it? Awesome. I will see everybody on Tuesday. And don't forget, I do have office hours on Monday. If you have any questions, I have office hours on Wednesday. Nobody showed up this week, so I just sat there and picked flowers or something. I'm sorry?
That was officer day.
I can't.
Yeah, sorry. When is the officer day?
When is
your officers?
Monday and Wednesday. Yeah, 1 o'clock on Monday and 4 o'clock on Wednesday. And if you need another time, just let me know. I mean, I'm usually in front of the computer anyway. Some people have noticed that I tend to answer Discord questions fairly quickly because Discord burbles at me. Hi. What was in the guest lecture? It's so I
tried watching the audio.